Hello, sir. Good evening, sir.
Yes, ma'am. Good evening,
You can
ma'am.
continue, sir.
Okay, ma'am, but you haven't started recording, ma'am.
Good evening, sir.
Yes, good evening. So let us start the discussion. So today, first of all, I would like to continue my discussion on the solutions for the multiple choice questions test, which I had given you last week. That is the 25 questions on electromagnetic induction. Okay, so in that test, I had given you 25 questions. So I had already discussed the solutions for first 19 questions. Now I am going to discuss the solutions for the remaining 6 questions. Okay. After that, we will start a new lesson on alternating current. So let me share my screen with you. Are you able to see my screen? Students, are you able to see my screen?
Yes, sir.
Okay, thank you. So this is the question number 20. A long conducting wire AH is moved over a conducting triangular wire CDE with a constant velocity V in a uniform magnetic field vector B directed into the plane of the paper. Full stop. Resistance per unit length of each wire is rho. Then you have 4 options. A constant clockwise induced current will flow in the closed loop. An increasing anti-clockwise induced current will flow in the closed loop. A decreasing anti-clockwise induced current will flow in the closed loop. And a constant anti-clockwise induced current will flow in the closed loop. Here you see, this is the arrangement. Okay, this is the arrangement. A long conducting wire AH is moved over a conducting triangular wire CDE. So this is the triangular wire CDE. Over this triangular wire, you can see this conducting wire AH is moved. Okay, and the resistance per unit length of each wire is rho. Okay, the triangular shaped wire. Okay, here you see the triangular shaped wire, and you have a horizontal wire as well, and this is actually moved. Okay, so now we have to find out in which that direction the induced current will flow, because here the conducting triangular wire CDE, okay, will be giving out a magnetic field, or you have a magnetic field directed into the plane of the paper that is represented by this thing. Okay, this into mark will tell you that the magnetic field is directed into the plane of the paper. Okay, so over the triangular shaped wire, another wire is moved. So due to that, you will be getting an induced EMF and you will be getting an induced current. Now, what is the direction of the induced current? And we have to check whether the induced current is constant or whether it is an increasing current and all. Okay. So from the 4 options, we need to choose the correct one. So for that, we shall see first the different basic concepts which you need to keep in mind. So here you see the magnetic field is actually directed into the plane of the paper. So the induced current actually flows in the anti-clockwise direction. This is the first concept which you need to know. Okay, whenever the magnetic field is directed into the plane of the paper, the induced current flows in the anti-clockwise direction. So this is the first thing which you should know. Now we need to find out the magnitude of the induced current. So that is given by I equal to E by R. That is from Ohm's law. Okay, I equal to V by R. So instead of V, we have to use E, that is the induced EMF. I equal to E by R. So E means here we should use the formula E equal to BLV. Okay, BLV. I think you know that formula very well. So E equal to BLV. So when a conductor of length L is moved with velocity V in a magnetic field, the induced EMF is given by BLV. So here what is the length? Okay. So here what is the length? That is FG. Okay. This FG. FG is the length actually. So that's why I have used instead of L, FG here. E into F, B into FG into V divided by R. R is nothing but the resistance. Here we have been given resistance per unit length of the wire, that is rho. So that means when you want to find out the total resistance, you need to multiply the resistance per unit length with the total length of the wire. Okay, total length of the wire, that is FG plus GD plus DF. That means the triangular portion. Okay, FG plus GD plus DF. So this total portion is actually covered. Okay, this total portion is actually covered, and the resistance of this total portion is rho into all these things. Okay, rho into FG plus GD plus DF. So how are we getting this? Because resistance per unit length multiplied with the length, it will give you the total resistance. So here FG plus GD plus DF. So here you see the wire AH is moved downwards. That means this FG, GD and DF are all increasing in the same ratio. Okay, this FG, GD and DF all increasing in the same ratio. Okay, so for that reason, actually the current will be constant. Okay, so this AH is actually moved downwards. Downwards means all these lengths DF, FG and DG. Okay, all these lengths actually increase, because when you move the wire downwards, the lengths actually increase. But here all the lengths increase in the same ratio. So due to that, the resistance remains constant. So I is also constant. So induced current flows in the anti-clockwise direction, and it is a constant one. So that is option D. Okay, a current, constant anti-clockwise induced current will flow in the closed loop. So that is a constant anti-clockwise current. Then question number 21. A thin circular conducting ring having n turns of radius r is falling with its plane vertical in a horizontal magnetic field B. At the position M and Q, the speed of the ring is V. Then the induced EMF developed across the ring is. Okay. Here a thin circular conducting ring having n turns of radius r is falling with its plane vertical in a horizontal magnetic field. So the position is given M and Q. At this position, the speed of the ring is V. Then the induced EMF developed across the ring. Okay. We have 4 options. We need to find out the right option. So here we need to see the direction of magnetic field. Okay. So and also the EMF formula we need to know. EMF E equal to BLV or BBL. Okay. Here L is nothing but twice the radius. Okay. From M to Q, the length is actually twice the radius. That is the diameter. So the EMF is given by BV into 2R. So that is 2R into BV. Okay, 2R into BV. Now the total EMF. Okay, total EMF is given by number of turns multiplied by this EMF, because in this coil you are having n number of turns, or in this ring you are having n number of turns. So you need to multiply the n, okay, with the EMF in order to get the total EMF. So the total EMF is n into 2R BV. Now you need to find out the force. F is equal to minus E into V cross D. That is minus of, okay, this V cross D, that will give you J cross K. Okay, minus J cross K. Minus J cross K. Minus J means negative direction of Y axis. That is quite obvious, because it is moved with velocity V in the downward direction. That means it is the negative direction of Y axis. So minus J cross K. So that will give you J cross K, that will be equal to I. So the force is along the positive X axis. So that means the Q is at lower potential. Okay, Q is at lower potential. Why? This Q is at lower potential. Okay, the force is along the positive X axis. So that's why here you are having the Q is at lower potential, and this is the answer. The answer is 2 RBVN, and Q is at lower potential. This is the answer for this question. Then question number 22. For the L-shaped conductor in the uniform magnetic field B shown in figure, the EMF across its ends when it rotates with angular velocity omega about an axis through one of its ends O and normal to the plane will be. Okay. So here you see you have the L-shaped conductor and it is rotating with angular velocity omega about an axis through one of its ends O and normal to the plane. And what is the value of that EMF? Okay, that thing we need to find out. So since the rod is rotating, you can see about the point O, the apparent length will be. So here you see L-shaped rod that is rotating means what is the apparent length? Apparent length means from here to here. Okay, from this point O to B. That is actually the apparent length. You can see from here to here. This is the apparent length. Okay, this L-shaped rod is rotating means the apparent length is O to B. So the apparent length is given by Pythagoras theorem. So this length, when you need to use this formula, square root of L squared plus L squared. That will be square root of 2L squared, and you need to take square root 2 common and outside, and this L squared, when you take the square root, you will be getting L. So square root 2L. So this length is actually OB, that is equal to root 2L. And the EMF is given by E equal to BLV. Okay. So V, now what is the velocity V? V is nothing but R omega, linear velocity equal to radius into angular velocity. Here radius is nothing but L. And of course you have omega. So V equal to L omega. Now you have to use B equal to BLV, E equal to BLV. So instead of V, you need to use this L omega. So BL squared omega is the EMF. Actually, you should not get confused. This length is nothing but the apparent length. Okay, this length is nothing but apparent length. Okay, on seeing the L, you should not get confused, because here already you are having a root of L squared plus L squared. Here also you are having L, but this L is different. This L is nothing but the apparent length. Okay, you should not get confused. So you can of course mention here this L. Okay, this L and this L is nothing but the apparent length. So apparent length is nothing but root 2L. So BL squared omega, instead of L square, you need to use the apparent length square. So root 2L the whole square, that will give you 2L square. Okay, so the correct answer is 2BL square omega. And this is how you need to answer this question. Then question number 23. A conducting rod PQ of length L equal to 1 meter is moving with a uniform speed V equal to 2.0 meter per second in a uniform magnetic field B equal to 4.0 Tesla. Directed into the paper, a capacitor of capacity C equal to 10 microfarad is connected as shown in the figure. Then you need to find out the charge value QA and QB. Okay, here you have plate A and the charge on plate A and the charge on plate B, you need to find out. Okay, and moreover you have options, other options as well. QA equal to 0 equal to QB. Okay, like that also you have. So conducting rod PQ of length L equal to 1 meter is moving with a uniform speed V in a uniform magnetic field B equal to 4 Tesla directed into the paper. So how you can proceed? So first of all, you need to find out the charge Q equal to C into capital V. This formula you know very well. I think you know very well, because C equal to Q by V. Capacitance value C is equal to Q by V. So here V is nothing but BLV. Okay, that is the EMF. So of course you have all the values. B is 4 Tesla, and the velocity is nothing but 2 meter per second, and L is 1 meter. So all these things you can substitute. So 10 into 10 power minus 6 into 4 into 2 into 1. So 80 microcoulomb. Okay, this charge Q is equal to 80 microcoulomb. So according to Fleming's right hand rule, the induced current flows from Q to P. From the diagram you can see the induced current flows from Q to P. How it is possible? Because I have already told you, when the magnetic field is directed into the plane of the paper, here this cross mark suggests this into mark suggests that the magnetic field is directed into the plane of the paper. So induced current flows in anti-clockwise direction. So that means here, okay, in this portion, the induced current flows from Q to P. Okay, that will give you the anti-clockwise direction from Q to P. Okay, from Q to P, the induced current flows. So that means plate A is positively charged and B is negatively charged. Okay, plate A is positively charged and B is negatively charged. So that means QA equal to 80 microcoulomb, QB equal to minus 80 microcoulomb. So that will be option E. And question number 24. The circular copper disc of radius 25 centimeters rotating about its own axis with a constant angular velocity of 130 radians per second. If a magnetic field of 5 into 10 power minus 3 Tesla is applied at right angles to the disc, then the induced potential difference between the center and the rim of the disc will approximately be B. Okay, will approximately be. So I think we already have discussed similar problems. Okay, a circular rim or a circular disc. Okay, when it is actually rotating, then we can actually find out the induced EMF between the center and the rim. Okay, the same formula we need to apply here. This formula E equal to BL squared omega by 2. Same formula. Okay, so you have all the values. B is nothing but 5 into 10 power minus 3 Tesla, and the length is actually 25 centimeter. Okay, that is 25 into 10 power minus 2 squared into omega. Omega is nothing but 130 radian per second divided by 2. So substituting all the values, you will be getting 20.3 millivolt. That is approximately equal to 20 millivolt. Okay, that is option A. Okay, that is option A. It's a straightforward solution actually, because you need to just write the correct formula and then you need to proceed. Okay, E equal to BL squared omega by 2. So option A is the right answer for this question. Then question number 25. A 1.2 meter wide railway track is parallel to magnetic meridian. The vertical component of Earth's magnetic field is 0.5 Gauss. Full stop. When a train runs on the rails at a speed of 60 km per hour, then the induced potential difference between the ends of its axle will be. So here also, the induced potential difference between the ends of its axle. Okay. So here also we need to use E equal to BVL. So B is nothing but 0.5 into 10 power minus 4. 0.5 Gauss. Okay, Gauss means it is 10 power minus 4 Tesla. You need to remember this conversion. How to convert the magnetic field from Gauss to Tesla? It is actually 10 power minus 4. 1 Gauss is equal to 10 power minus 4 Tesla. So using that you can find out E equal to BLV. B is 0.5. Okay, and L is 1.2 meter. And V is 60 km per hour. 60 km per hour, you can convert it into meter per second. So 5 by 18. 60 into 5 by 18. And the EMF is nothing but 10 power minus 3 volt. So this is option C. Okay, this is option C. Okay. Do you all understand the solutions for this problem, students? Students, do you all understand the solutions? Yes. Shall we move forward?
Yes, sir.
Okay. Now we are going to start our new lesson. Okay. So the new lesson is actually alternating current. The new lesson is alternating current. Does anyone know about alternating current? Students? Alternating current. Does anyone know the meaning of this? Yes. Anyone can tell. Okay, whatever you know about this alternating current. You can simply unmute yourself and you can talk. No issues. Even if your answer is wrong, then it's not a big problem. Okay. Only thing is you need to try. Students, anyone can tell. No issues. Please don't hesitate. What is the meaning of alternating current? Anyone can try. No issues. Okay. I will give you some diagrams. Based on that, you try to tell me. Okay. Now, students, you have four diagrams here. Okay, four graphs. Can you observe any difference here among the four graphs? Can you observe any difference? I have given you four graphs now. So can you observe any difference among the four?
Sir,
Yes.
the direction of current is changing, sir.
In which cases?
Sir, in second, third, and fourth case.
Okay. In the first thing, in the first case, what do you observe?
It's in uniform motion, sir.
In the first case, you can observe there is no variation of current with respect to time. Okay. So, in the first case, you can observe that the current doesn't change its magnitude or direction with respect to time. There is no variation in the magnitude or direction of current. So, in the first case, there is no variation of magnitude or direction. That means this is called direct current. Okay, this is called direct current. The first case, no variation of magnitude and direction. Okay, because the direction and magnitude remains the same with respect to change of time. So when the even though the time changes, there is no change in magnitude or direction of current. So this first case is called direct current. Okay, but in all the other cases you see, so in y-axis you can have EMF or current. Okay, EMF or current, anything you can have on the y-axis. On x-axis you need to have time. Okay, so here you see the magnitude and direction changes periodically, be it induced EMF or current. Okay, whatever it is on the y-axis, the induced EMF or the current, it changes periodically both magnitude and direction. Okay, here also you can see, here it is actually a sinusoidal variation. This is called sinusoidal variation. Here it is called co-sinusoidal. Okay, so this is sinusoidal variation, this is co-sinusoidal variation. Nothing but simply you can say this is a sine wave and this is a cosine wave. Okay, so this is a sine wave and this is a cosine wave. Cosine wave means it starts from maximum value and the magnitude and direction changes periodically. Sine wave means it starts from 0 and magnitude and direction changes periodically. You know very well, sine 0 value is 0 and then sine 30 degree it is 1 by 2. After that you will be having sine 45 degree 1 by root 2 like that. Okay, so sine wave, cosine wave. So both in both things you can actually observe the variation of magnitude and direction periodically. Okay, and of course here also it is a triangular wave. Here also you can see that the magnitude and direction actually varies. Okay, periodically. So all these three cases are examples for alternating current. Okay, so alternating current, how you can define? So when the magnitude changes continuously, okay, it can be voltage or current. It can be voltage or current whose magnitude changes continuously, magnitude and also direction. Okay, whose magnitude changes continuously. Whose magnitude changes continuously and the direction also reverses periodically. this is the meaning of alternating current. Your magnitude and direction both should change, okay, or any one, but usually the magnitude and direction both changes, okay. The voltage or current whose magnitude changes continuously and direction reverses periodically, that is called alternating current, okay. Do you all understand the meaning of alternating current now? Students, do you all understand the meaning of alternating current now?
Yes, sir.
Yes, sir.
Okay, okay. Now we shall move on to the various definitions used in AC circuits. Okay, the various definitions used in AC circuits. So for that, I should draw this diagram. So here you see current is along y-axis and time is along x-axis. Okay. So here I am marking the time period. Okay. This is T/2. This is 3T/4. And this is T. Okay. Right. So here you see this is the current along y-axis and time along x-axis. Of course, both these cycles should be symmetrical. Okay, you should not think that this positive cycle is a little bit narrower and this is broader. Actually, both should be symmetrical. Since I am drawing it manually, okay, you may observe these kind of variations. So please ignore that. Actually, both these half cycles should be symmetrical. So now we have some definitions. Okay, we have some definitions. Here, standard definitions. What are the definitions? We shall see one by one. First thing is instantaneous value of AC. Okay, instantaneous value. So what is meant by instantaneous value of AC? So at any point, okay, at any point you can find out the current. So here I am actually considering the instantaneous value of current, but you can also have voltage along y-axis. So in that case, you can find out the instantaneous value of AC voltage. Okay, here I have taken one example, that is current along y-axis and time along x-axis. Here I am considering the instantaneous value of AC current. So what is the instantaneous value of AC current? So along the curve, okay, You can consider any point. Okay, you can consider any point. So be it here, okay, at this point or at this point or at this point, okay, any point you can consider, okay, at this point or at this point, at this point, this point, any point, you can find out the value of current. So that is actually called the instantaneous value. At any point on the graph, you can find out the value of current here, or if voltage is along y-axis, you can find out the value of voltage at any point along the curve. At that instant of time, it is called the instantaneous value. Okay, that is called the instantaneous value. And here you can see in this example, your current is actually varying sinusoidally. So the equation is given by I equal to I naught sine omega t. Okay, this is the equation for this graph because it is the sinusoidal variation of AC current. So the equation is given by I equal to I naught sine omega t. Okay, and we shall move on to the second definition. We shall move on to the second definition, that is amplitude of AC. Okay, amplitude of AC, that is represented by I naught. Okay, so amplitude of AC, and that is represented by I naught. Okay, so what is mean by I naught? The maximum value of AC is defined as amplitude or peak value. So here you see at this point you have the maximum value. Okay, at this point you have the maximum value, and this point you have the maximum value. Okay, so the maximum value means the maximum possible value. So here at this point and here at this point, it is a positive maximum and it is the negative maximum, but the maximum value of AC, it is defined as the, okay, I can change colors. So the maximum value of AC is known as amplitude. Okay, the maximum value of AC current here actually. So maximum value of AC, or it is otherwise called amplitude or peak value. Okay, it's otherwise called amplitude or peak value. So at this point and this point, okay, you can find the maximum value, that is called amplitude. So this maximum value actually becomes maximum twice in one cycle. Okay, one complete cycle. So from here to here, you are having the negative maximum, and here you are having the positive maximum. So it becomes maximum twice in one cycle. Okay, the peak actually at times maximum twice in one cycle. So that is the thing which you need to understand. And the next thing is time period. Time period of AC. The next definition is time period. Okay. So what is mean by time period? The time taken during which the alternating current completes one cycle. So from here to here, okay, this is one complete cycle. From here to here you see, okay. So from here to here, it completes one cycle, okay. So the time taken to complete one cycle. So from here to here, it completes one cycle. What is the time taken? The time taken is actually called time period. So now we shall define it. The time taken for AC to complete one cycle. Okay. This is called time period. Do you all understand? Do you all understand the definitions up to this point? Any doubt you have? Students, do you all understand this? Any doubt you have?
No doubt.
Okay, I hope you can understand all these things because these are very, very simple. And next definition we shall proceed, that is frequency. Okay, frequency. Time period is actually represented by the letter T. Okay, by the letter T. So that's why here this is 1/4 of the total time period. Okay, so from here to here, you are having the complete cycle, and this is 1/4 of the cycle. So the time taken is T by 4. Here it is 1/2 cycle, so the time taken is T by 2. And here you have one complete cycle, the time taken is T, and here it is 3/4 of the total time taken to complete the cycle, so that is 3T by 4. So usually it is represented by the capital letter T, and I think you all know very well about this. Now let us move on to frequency. The next definition is frequency of AC. That is, yep. So frequency means number of cycles completed by AC in 1 second. Okay, number of cycles completed by AC in 1 second. It is called frequency. Okay, number of cycles completed by AC in 1 second is called frequency. So actually, when you have a coil, okay, coil rotating in a magnetic field, the number of rotations made by the coil in 1 second is called frequency. Okay, so in general, the number of cycles completed by AC in 1 second is called frequency, and the frequency can also be written like this, that is the reciprocal of time period. So F is equal to 1 by T. Frequency is nothing but the reciprocal of time period. So now in our houses, we are actually receiving AC, that is alternating current. We know the frequency of the AC received in our houses. AC means alternating current. We know the frequency of the alternating current received in our houses. Yes, students. The frequency of AC received in our houses, we know the value of it. We know the value of it. It is actually 50 hertz. Okay, 50 hertz. That means in 1 second it completes 50 cycles. Okay, in 1 second it completes 50 cycles. So in our houses we are receiving alternating current at the frequency of 50 hertz. Now we shall move on to the next definition, that is angular frequency. Represented by the letter omega. So omega is nothing but omega equal to 2 pi into F, that is equal to 2 pi divided by T. Okay, this is the angular frequency. Okay, this is the angular frequency. And of course, this is the next definition. Right. Now we shall move on to some important definitions of AC that will be useful for us in solving the numerical problems. Average and RMS values of AC. So average and RMS values of AC. This is the next definition. So what is mean by average value or mean value? So over any half cycle, okay, over any half cycle, that means either positive or negative, you can see. So this is one half cycle, okay. This is one half cycle. So over any one half cycle, be it positive or negative half cycle. So it is the value of DC which would send the same amount of charge through a circuit as it is sent by AC through the same circuit in the same time. Okay. I think you should not confuse yourself with the definition. Okay. So we shall see the definition by one equation. So now I shall write this equation. So the mean value of current, AC current, is represented by this symbol. Okay, this symbol represents the mean value. So this is equal to integral 0 to tau I dt divided by integral 0 to tau dt. This is the average value of current. Okay. Here, what is integral 0 to tau I dt? That we need to define now. So I will do it with a different color. So this 0 to okay. So here this 0 to tau I dt. What is the meaning of this? So this is nothing but the charge flowing through the AC circuit. This is nothing but area under the IT graph. Okay, area under the IT graph, current versus time graph. This is integral 0 to T I dt. Okay, area under the IT graph means you can see this area. Okay, this area, so this area, also this area. That is integral 0 to tau I dt. Area covered under this IT graph, current versus time graph. That will give you the charge flowing through the circuit. Okay. So the mean value is given by this equation. I is equal to, mean value of I is equal to integral 0 to tau I dt. That is area under the IT graph divided by 0 to tau dt. Integral 0 to tau dt. Okay. Now using this formula, okay, using this formula, we shall find out the average value of I equal to I naught sin omega t over the positive half cycle. So average value or mean value, okay, average value of I equal to I naught sin omega t. When you have this current, so that is represented by this circuit, I equal to I naught sin omega t. So you take this circuit. So for this circuit, for the positive half cycle, I am going to find out the average value. Okay, for the positive half cycle. Let us see how we can calculate. So average value of I equal to I naught sine omega t over the positive half cycle. Over the positive half cycle. So this we are going to find out. For that I need to use the equation I average is equal to integral 0 to t by 2. Okay. Integral 0 to t by 2 I naught sine omega t whole divided by integral 0 to t by 2 dt. Do you know why we are using the limit 0 to t by 2? Can anyone tell me? Can anyone tell me, students? Why we are using the limit 0 to t by 2? Yes, students, very simple. You can try.
So it's a half cycle, sir.
Yes, for the positive half cycle only we are using. Okay. Even if it is the negative half cycle, the same limits are applicable. 0 to capital T by 2. Okay. Even if it is the negative half cycle, the same limits are applicable. So be it the positive half cycle or the negative half cycle, you can use this. Okay. So you can use the same limit 0 to capital T by 2. And now when you integrate this, what you will get? Okay, when you integrate this, what you will get? For the numerator, okay, for the numerator, when you integrate this, you will be getting minus cos omega t divided by omega, and you should use the limits 0 to t by 2. Okay. Into I naught. I naught is the constant, so you can take this out of integration. So I naught. In the denominator, you are having integral 0 to t by 2 dt. So that will give you t by 2 in the denominator. Because when you integrate this, integral and d will be cancelled. Okay. And when you integrate this, you will be having t only. So when you apply the limits t by 2 minus 0, that will give you t by 2 in the denominator. So here, now what you have to do, you have to apply the limits. Okay. So after applying the limits, what you will be getting? Okay. Let us see that. So this omega, sorry, this here you won't be having t. Okay. Here you won't be having t, will be having just omega. So here you are having omega. So what you can do is we can take minus common. Okay, you can take this minus common, and omega is also common. So this minus I naught by omega, you can take common within the bracket cos omega t by 2. Cos omega t divided by 2 minus cos omega into 0 whole divided by t by 2. Okay. So you will be getting this, and when you simplify this, what you will be getting? You will be getting 2I0 divided by 5. This is the average value of I equal to I0 sin omega t over the positive half cycle. Okay. And we have found out the average value over the positive half cycle. And over the complete cycle, we can write the equations. Okay. Over one complete cycle or over one cycle, we have some formulas. So average value of sin theta is equal to average value of sin 2 theta. Okay, this will be 0. Okay. Similarly, average value of cos theta equal to average value of cos 2 theta will be equal to 0. These are some of the standard equations. You can memorize this. So average value of sin theta cos theta, this will be equal to 0. And the average value of sin squared theta, this is equal to average value of cos squared theta, this is equal to 1 by 2. Okay, these are some of the standard formulas or standard equations which you should know. Okay, for the average value. And we shall stop with this. Okay, for this class, and we shall continue with the alternating current concepts in our next class. Okay, I hope you all can understand the concept whichever we have discussed up to this point. If you have any doubt, you can ask now.
No doubt, sir.
Okay, so let us stop with this one, and we shall meet again in our next class. Thanks for joining.
Thank you, sir.